is heat treatment process. Why we have to go for heat treatment process? Whenever we go for a material, any composition, we can make a different composition of metals, but if we want to improve the properties in that metal, we have to go for some heat treatment process. So from that we can improve the characteristics and the property of the metal. Okay, first we see the definition for heat treatment process. What is a heat treatment process? Controlled heating and cooling of metal to change its property and performance. So here we go for heating and cooling at a controlled level. Okay, we go for, if we want to heat a metal, we go for controlled, like a controlling process. Okay, next, what is the purpose of doing a heat treatment process? To improve the toughness. See, we have some mechanical properties. Yeah, what are the important properties? Toughness, ductile, hardenability. This all we called as mechanical properties. So that we call as characteristics of the metal. So we have to go to improve that properties. We have to undergo the heat treatment processes. So each and every heat treatment process has a different property outcome. Okay. Now first, to improve the toughness, to improve the hardenability, to increase the ductility, okay, to improve the machinability, to refine the grain structure, to remove the residual stress, and to improve the wear resistance. Okay, first we go one by one. To improve the toughness, okay, so listen here, the material should have the toughness by using, go for some heat treatment processes. Okay, next we go for hardness. Okay, why we go for hardness? The material should not get wearness. Okay, second, the material should have to able to cut another metal. So if we go for to improve that property, going from, we can receive that property using the heat treatment process called quenching. Okay, next we go for ductility. A ductility is another mechanical property, a very important mechanical property. So we can receive this property by go for heat treatment process by using some annealing and normalizing process. So okay, to improve machinability, we go for annealing process. To refine a grain structure, what thing is, when we go for some machining process, the material is going, for example, go for cold rolling process. In that, the material structures, which you can see, the materials is inbuilt with number of structures together and getting a bonding strength. So if the metal is going to, what thing is, the metal is going to crush on another structure metal by using a cold rolling process, the material gets structured. So the structures, grain structures may be just crushed, so the dead cells may happen. So we have to go for refine that grain structures. So we have to go for heat treatment process. Residual stress. For example, we go for a press work. Okay, we go for press work. We go for the stress is inbuilt inside your metal. If we allow the metal to be inside the metal, if we allow the stress to be inside the material, so if you go for the application demands some load. If the load is increased, already stress inside the metal causes the metal failure. So we have the importance to remove the residual stress by using an annealing process. So we have a lot of important terms to improve the properties by go for heat treatment process. Okay, next, what is heat treatment process? We told that controlled heating and controlled cooling of a metal is to change its property and performance. Okay, if you go for heat treatment process, what is going to happen? Change in microstructure, change in chemical composition. Right. Now we can see a diagram. So this is a diagram, for a simple diagram that we're going to draw in between a temperature and time. Okay, on a vertical I'm going to plot a temperature, and horizontal I'm going to plot a time. Okay, when always the heat treatment process undergoes 3 stages. First one is heating, second one is soaking period, or we call it as holding period. Third one we go for cooling. Okay, first we go for heating process. So each and every metal has a desired temperature for heating. Okay, for cast iron we have some material temperature. For aluminum we have some material temperature. For steel we have some material temperature. So based on that material composition, we are going to fix some temperature as a final temperature. We are going to heat the metal. So automatically the time gets increases. Automatically the temperature gets increases. So we can see this curve shows the heating curve. After the material reaches its destination temperature, we have to go for soaking period. Okay, what is the purpose of soaking period? Whenever surface of the metal will get the temperature easily, so that temperature has to reach to your end of your, that is middle of your material. So we have to allow the temperature to move inside your surface of inside your part of your material. So we go for soaking period. If you allow, the soaking period is fixed depend upon your size and composition of your material. Okay, next we go for cooling process. Okay, we have three types of cooling process. One is slow cooling, second one is moderate cooling, and third one is rapid cooling. So depend upon the cooling, you're going to get the properties of the material. Okay, see three stages. One is, again tell you, this is a curve. We have three stages: heating and soaking period and cooling. Stage 1 is heating, stage 2 is soaking, and stage 3 is cooling. Next, now you can see the picture that is seems to be, we call this as 1 minute. Okay, so you can see a iron carbon diagram. This is a very very important diagram, depend on a steel and cast iron composition. Okay, here always we go the horizontal, we go, it seems to be called this as composition. Okay, and this vertical we're going to plot a temperature. Okay, here horizontal we're going to plot the composition. We're going to increase the carbon percentage. Going on, we're going to increase the carbon percentage. Okay, let me explain the iron carbon diagram. Okay, first the what thing is, we have three types of reaction is taken place in iron carbon diagram. The first one is Utitoid reaction. I just placing the cursor. This we called as Utitoid reaction, and this we called as, this point I'm going to place here. This point is called as Utic reaction, and this point is called as perotic reaction. Okay, this three reaction taken place in iron carbon diagram. Okay, let me come for composition, and this is the horizontal line. In the horizontal line, the composition is going down, increasing. Okay, next that is, first you going to, this horizontal line is divided into two parts. One is steel part and cast iron part. Okay, first 0% to 0.008% of carbon, we call the materials is called as pure iron. Above 0.008% to 0.83%, 0.008% to 2%, we call this as steel, and 2% to above percent we call as cast iron. So first we see three types of reaction. One is Utitoid reaction and Utic reaction. Third one is perotic reaction. Here the horizontal is now divided. Horizontal line that defines composition is divided into two parts. One is steel, second one is cast iron. That is 0.008 to 2% we called as steel, and 2 to above percent we called as cast iron. Further, this steel and cast iron is divided into two parts, A and B. So A shows thus hypo-Utitoid steel, and B shows thus hyper-Utitoid steel, and C shows us hypo-Utic steel, and D shows us hyper-Utic steel. Let me show in the diagram. And 0.008 to 0.83% we call the material as hypo-Utitoid steel, and 0.83 to 2% we call this as hyper-Utitoid steel, and 2 to 4.3% we call this as hypo-Utic steel, and 4.3% to 6% we called as hyper-Utic steel. So hyper-Utic cast iron. So sorry, 2 to 4.3% we call this as hypoedetic castration, and hyperedetic castration we call as 4.33% to 6.67 percentage. Okay. Now you can see this is the first. You can see the three reactions: eudotic reaction, eudotoid reaction, and eudotic reaction and periodic reaction. Okay. Now we can see the structures present in iron carbon diagram, that is perlite, ferrite, and perlite Fe3 we call as cementite, and here you can see arsenite, and this we call as arsenite and cementite. Okay, this is we called as iron carbon diagram. Okay, let me explain in detail. Okay, that is 0.008 to 0.83%. The structure will be as perlite. Fine, first, that is initially it is called as perlite. When you're going on eating, the structure is interchanged to ferrite. So first you have to keep on mind, depend upon your temperature rise and depend upon your composition, your material structure is going on changed. So each and every structure is having a different properties. So here you're going to at 0.832, again you come on B section, that we called as hypoedetic steel. Okay, here 0.83% to 2%, we call this as a hyperedetic steel. Here initially it seems to be called as perlite, and finally it changes to Fe3 we call cementite. Again I am going to eat a metal, the cementite changes to arsenite. Here at section A, that is hypoedetic steel, that is 0.08 to 0.83. Here initially it seems to be perlite, converted into ferrite, again they convert to arsenite. Here 2% to 4.33% we call as hypoedetic castration. Here initially you can see the perlite plus liberite and cementite, finally go for arsenite. Here again arsenite plus cementite. Here you can see liberite and cementite, and finally arsenite plus cementite, and finally getting the cementite here. Now we come for again to heat treatment process. Here the heat treatment process is convert. Just a minute, I can show this in detail. Here as you call as heat treatment process, it seems to be a branch diagram. The heat treatment process is divided into bulk heat treatment process or full heat treatment process. Again further divided into a surface heat treatment process. Now we are going to discuss here the full heat treatment or bulk heat treatment process. So let me see what are the important heat treatment process here. The annealing, normalizing, and hardening. We called as main three different types of heat treatment process. So annealing is further divided into full annealing, recrystallization annealing, stress relief annealing, and speculation annealing process. Here the annealing we go for is called a slow cooling process, and normalizing we call this as a moderate cooling process. And hardening and tempering. Okay, and hardening process we called as tempering process as tempering process. Here you can see a structure diagram here, and this is the point where the eudotic reaction taking place. Here as you can see at 0.83% the eudotic reaction taken place. At 723% Celsius temperature, this point we called as eudotoid point. A temperature at which the eudotoid reaction taken place we call as the eudotoid temperature. Here based on this the reaction is taken place. So above the A3 temperature the full annealing process taken place, and above the A3 process you can see a normalizing process taken place. You can see the first full annealing process. So here first the annealing process we call this a slow cooling process. Okay, slow cooling process, And second, you can see when you go for slow cooling process, what is going to happen is the material, when you go for slow cooling, the structures when going to set homogeneously inside your material to allow for long duration of cooling. Here first, the process of slow cooling is called as known as annealing. The material are heated above the critical temperature. First point, the material we call the annealing as slow cooling process. Here the material is heated above the critical temperature. Third, the time taken for cooling is is very slow cooling process. You can see the slow cooling process. Okay, the cooling is taken place at 30 degree per hour. Otherwise, the annealing is called as furnace cooling process. Here you are going to heat the metal to above a critical temperature. Then, after the material is reaches to distillation temperature, the material is go for soaking period. That we called as second stage of heat treatment process. Here, the material is cooled. What is maintained for a long period at the same temperature, so that the surface and middle part of your component reaches the same temperature. After the soaking period is over, the material is cooled slowly inside the furnace itself by setting your furnace to reduce the temperature for 30 degree per hour. Now the temperature gets the reducing temperature now. Now, if you go for slow cooling process, what changing is going on inside your structure is the material cools homogeneous, and the structure between the one bonding strength between one structure and another structure, the material will give good bonding strength. So that the material ductility property gets increased. We can see next cooling process. So you can see here the want to make hypoheated steels less than 0.83 carbon are heated above upper critical temperature, and hyperductoid above 0.83% are heated above lower critical temperature. Okay, now we come for process annealing process. So we have four types of annealing process, that is annealing, full annealing process, process annealing, stress relief annealing, recrystallization annealing. Here we are going to discuss a process annealing. Here we are going to heat the metal to above 550 degrees Celsius to 650 degrees Celsius. This is the temperature duration for any material. So you're going to, for example, you take a material as 600 degrees Celsius to heat. So you're going to heat the metal to 600 degrees Celsius and maintain the temperature for a certain period that we call a soaking period, stage 2. Then you go for slow cooling. The cooling is done inside the furnace. Cooling is done inside your furnace. That is set 30 degree. That is going to reduce a temperature as 30 degree per hour. So you can see the microstructure of a material. So you can see the microstructure of the material. This we call as coarse perlite, and this is called fine perlite. This is called coarse perlite and fine perlite. Next, we go for recrystallization annealing. So okay, what is the purpose of doing a recrystallization annealing process? Here, any material is going for manufacturing process. Without manufacturing process, we can't derive the proper material, correct? So if we take two types of manufacturing process, one is press work, or you go for cold rolling process. Here the material go for cold rolling process. The material is going to crush to bring the metal to a defined shape. In that, the structure is also going to crush. While the crushing of structures, the material structures gets dead cells. So we have to improve the structures inside the dead cells. So we go for recrystallization annealing process. Here we're going to heat the metal for 500 to 650 degrees Celsius and maintain that temperature for a certain period, that we call soaking period. Then it's going to cool it. While you're going to cool it, what is going to happen inside the structure is, here the structure is going to refine and form into new structure and gets bonding between one structure to another. If it is not done, the dead cells between the structure will not get bonding strength. So there you can see what is vacuum space is created. So if the load is applied in that part, without the dead cells, with the dead cells, there is no bonding strength. The material causes to failure. So we have to refine that those dead cells. You go for recrystallization annealing process. So this is in here. So this is the, you can see the structures for cold rolling grain structures. You can see irregular structures. After annealing, the structures are arranged into a defined and very closely bonding strength structures. So this we call recrystallization annealing process for our treatment process or cold rolling or a press process. You can go for recrystallization annealing. I can show now the next slide. Now stress relief annealing. Here this is done to relieve the internal stress inside your material. Okay, this is another third type of heat treatment process. Here I going to after annealing, after the material is being to the part, the material finally go for heat treatment process. Here the material ductile property is improved, as well the stress inside, the internal stress is created inside due to the manufacturing process that is relieved. Here I going to heat the metal for 500 to 650 degrees Celsius. Then that temperature is maintained. For example, I take as a specimen temperature for 550 degrees Celsius. Here I going to heat a metal for 5 degrees, 500 degrees, 50 degrees Celsius. Then that temperature is maintained, that we call it stage 2 soaking period, until the entire component reaches the same 550 degrees Celsius. The soaking period is maintained. After soaking period is maintained, the material reaches the same temperature, the soaking gets stopped. Now we go for cooling process. Now the temperature is cooled inside your furnace itself. That's a ratio for 30 degree per hour or 10 degree per hour, depend upon your fine structure requirement. Now if you do so, the internal stresses, why the internal stress is created? For example, any press work, you can see the press is going to impact your material in the higher impact load. So this is a load. Whenever load is created in the metal, the automatically material gets stressed. So internal stress is created. Without relieving that stress, we go for the application work. The application demands a load. That load increases stress as well. The stress already inside your component, the stress is increased a lot. So that leads to the material to go for failure. So we have to remove the internal stress. So you're going to heat them for 5 degrees Celsius. Then the temperature is maintained for a period of hour, that we call soaking period. Then allow it to slow cool to room temperature inside the furnace. So this, I told you that already, this all annealing process is called as furnace cooling process. The method is very cheap and more rapidly used. Hence internal stress are removed. Now I can see the synchronization annealing process. Okay, here the same thing is going to happen. You can see the structures inside your material. You can see this is structure of the metal, and this is the point where your synchronization annealing is taken place. Here it is also, it has a specific treatment process to give for high carbon steel. Here the material is increasing the ductility. What is the purpose of doing this annealing process is to improve the ductility property. Here the metal is going to be above the A1 temperature and maintain the temperature for a certain period, and you go for soaking period, then go for cooling process. So this we call as synchronization annealing process. Now I just going for normalizing process. Okay. Now, what is normalizing process? This we called as moderate cooling process. Normalizing is what I think. Here we go to normal cooling process or moderate cooling process. First, we discuss the metal for the pretreatment as slow cooling process. Here normalizing is a moderate cooling process. Normalizing, okay, is one thing. When you go for the economic way, the normalizing process seems to be better because when you go for annealing, we have to go for furnace cooling process. The furnace cooling process, if you go, we have to give the power source and human source for furnace to work, to cool also. Here we are going to heat the metal and we're going to maintain temperature and we're going to take the component outside and we're going to cool in the air. That we call normalizing process. Let me see this in detail. Here normalizing is a similar to the full annealing, but cooling is done by chill air rather than furnace. Here what's the purpose of the normalizing? Refine the grain size, improve the mechanical property, to improve strength of the steel. Here the material is heated above 40 Celsius to 50 Celsius above the upper critical temperature. The temperature is maintained for a period of hour. I show this slide in detail. Then allow it to cool slowly to room temperature. But cooling is done in a chill air. Here you can use a fan or you can use a blower to cool. The normalizing process consists of ferrite and pearlite for hyper-eutectoid steel and pearlite and cementite for hyper-eutectoid steel. And you go for next slide. Here you can see different structures that you obtained in a normalizing process. This is a structure you can see by microscope. You can't see these all structures in the naked eye. If you go for after your material, your specimen is finished its heat-treatment process, normalized heat-treatment process, you can keep this specimen in a microscope and you can view this type of structure. This we call as normalizing microstructure. These all the structure depend upon your composition of material. The structure gets changed. And we go for hardening process. This is very very important hardening process. Let me come here. Okay, hardening process. Here the hardening is another important heat treatment process. Why we have to go for hardening process? Hardening process improves the hardness of the metal. Here you can see medium and high carbon steel above 4 to 1.2% of carbon can be heated until red hot and then quenched in a water, producing a very hard and brittle material at 723 Celsius. Okay, next you come here. The hardening. Okay, the thermal. Okay, what is if you go for hardening? What all the defects is taken is thermal stresses is created, and that should be avoided. Second, before we go for hardening, we have to go for preheating the temperatures about 600 to 600 degrees Celsius. Next, in the case of high-speed steel, the holding time will be shorter when the hardening temperature is above 1100 degrees Celsius. If the holding time is prolonged, the microstructure problems like grain growth can arise. So you can see a T diagram, as temperature diagram here. Okay, this curve we call this as, I will show more clearly. So this is the curve. You can see this diagram. Okay, and this we call as S curve or we call as stability curve. Okay, now for example, if the hardening is done by quenching process, what is going to happen is, if the temperature difference, when you're going to take the metal at a certain higher temperature, you can drop into quenching medium. If you maintain a quenching medium 30 degrees Celsius, here the temperature duration is very long. If you're going to drop it, the material gets the thermal shock. That thermal shock causes the material to crack. So we have to avoid the thermal crack. Here you can see I going to reduce the duration of time. So I going to improve the temperature of quenching medium. So I going to make the quenching medium. Now if you're going to put the component inside, I going to drop it. Okay, I can drop it. You can see two curves. First surface which is contact with the quenching medium gets cool fast, and the temperature the inside your center of your component gets cool later, and this shows the first curve. You can see the surface cooling curve, and the second curve will shows the center part of cooling curve. Here the curve is drawn between your time and temperature. So this is the time duration between the surface and center to cool. Center to cool, and this is the S curve. Okay, just continue now. Now, quenching process. What is a quenching process? An instant cooling process is called as quenching process. Here, what is going to happen is a rapid cooling process. If we want to improve the hardness of the metal, we have to go for quenching process. Here, you can see a sketch of different quenching medium. Okay, the time taken for quenching medium. Here, we're going to plot at vertical on temperature, and horizontal we're going to plot time. Here we're going to use different types of quenching medium. So each and every quenching medium takes a duration of time to cool. Here the process of fast or instant cooling is known as quenching process. The cooling is done by contract the material with the quenching medium. A quenching medium has a solid, liquid and gas. Here first the water, we can see different types of quenching medium: water, air, polymer, air vacuum and salt bath. Water is the best quenching medium ever because it takes very short duration of time. Next, types of quenching medium: a brine, that is salt bath, water, oil, air on, or a turn of furnace is called as quenching medium. Here, quenching medium, the setting of quenching medium depend upon the boiling point of, if you go inside a quenching medium, three different points you have to maintain. That is, first one is boiling point and viscosity of quenching medium and desired rate of cooling. The boiling point, that is, if the boiling point should be high and more when compared to your temperature of your metal. If the boiling point less the temperature of metal, the oil gets splashed. So first stage, the quenching medium has three stages: vapor jacket stage, vapor transport cooling stage, liquid cooling stage. Vapor jacket stage, when you're going to put the metal inside a quenching medium, a gas is surrounded, the gas is surrounded to your metal. The vacuum gas is surrounded to your metal. A vacuum gas is surrounded to your metal. Here, that gas, that smoke, what is surrounded as a vacuum jacket, a vapor jacket to your metal. So that vapor, when you're going to put a high temperature metal drop into water, just an example, you can see a gas or vapor is surrounding the component, that we call as vapor jacket stage. Here the cooling rate is very low. Vapor transport cooling stage. Here now the vapor all evaporated. Now the temperature, the component touches to the quenching medium, the temperature gets reduced. Now the liquid cooling stage. Now the temperature and the component gets the same temperature. The medium and component gets the same temperature. Now you can see the quenching medium. The outer surface is the surface of the component, and the center we called as at high temperature when compared to your surface. So this is we called as a temperature difference between your surface and the middle part of your component. And Jomi and quench test. Here Jomi is a Dr. Jomi has invented this test. So this is quench test. Here we're going to take a specimen. The specimen height is 11.6 mm and 25.4 mm, and diameter will be seems to be as 25.4 mm. We're going to heat the metal and we're going to place this specimen vertically. We're going to give the heat on one side of the component. So the temperature will be passed from bottom to top. Now I'm going to splash the water. Now the touches the water, the surface which touches the flame, same surface such as the water, that part will be hard and high and hard when compared to the top end. This we call the, and we can go for, we can using your hardness test, we can see the hardness difference between your the quenched end to a non-quenched end. So this is the hardenability. Hardenability should not be confused with the ability to have high hardness. The material with a low hardenability may have high surface hardness and compared to another sample. Okay. So the material with high hardenability can be cooled relatively slowly to produce 50% of martensite. The martensite is a structure which has higher hardness. And a material with high hardenability has a nose of CCT curve to the right. So this we call as CCT, the controlled cooling temperature curve. Continuous cooling temperature. Okay, tempering process. For tempering, if you go for quenching process, the material become hard, but the material will be go for brittleness. So we have to remove the brittleness. So we go for tempering process. Here the material is heated to 250 to 650 degrees Celsius, then maintained for a certain period. The material then you can see we go for slow cooling process. This we call as tempering. First, you're going to heat the metal to 250 to 650 degrees Celsius. That is a very already quenched metal that you go for tempering process. Then they maintain the temperature for a certain period. Then you go for slow cooling process. Next, tempering. And to remove some of the brittleness from the hardened steel, the tempering is used. The metal is heated to the range of 220 degrees to 300 degrees Celsius. And tempering colors are an indicator of temperature on polished metal. The color range from yellow to brown to violet and blue. Okay, first before tempering you can see martensite structure. After tempering you can see the ferrite and cementite structure. Here this we call tempered martensite structure. Okay, this is we called as a graphical definition of tempering. Okay, we have two types of tempering process: matte tempering process, second harsh tempering process. The matte tempering process we getting the martensite structure, and harsh tempering process we getting the binite structure. Here we are going to heat the metal. After we are going to cool the metal drops the temperature. After that, here we are going to heat at a quenching medium above the martensite structure starts temperature. So above 300 degrees Celsius. To avoid the thermal shock, we are going to maintain the temperature. Metal gets dropped from 800 degrees Celsius to 300 degrees Celsius. Then the component will reaches the quenching medium temperature. If we allow the temperature to maintain inside the furnace, the component inside the furnace, that leaves for a long period, the material changes to binite structure. If we are going to cool it inside the furnace, we are going to cool inside the quenching medium. Then you're going to take the component again. We're going to cool it slowly. The material seems to be martensite structure. So this curve we call as nose curve, and this we call as otherwise we call as a S curve. And this is the duration where the structure is going to change. Here this curve, the structure starts to transformation starts, and this curve shows the transformation end. So if you're going to maintain the component inside the furnace, it's inside your quenching medium itself, the structure leads to binite. If you're going to take the component after the component reaches the quenching medium material temperature, again you're going to cool it, you can see the martensite temperature. Okay, so we're going to get in matte tempering, we call this matte tempering. Okay, we're going to get a martensite tempered structure. Here you go for harsh tempering, you're going to get a binite structure. Matte tempering process, you're going to get the martensite tempering structure. Thank you.